Second?
I have two. I have two labs. Here. I have one lab here too. Good. Thanks.
All right. And we go till when, just to be aware? Till the top? I know we're a little bit behind, that's why I'm
Yeah,
asking.
so if you can, that's great, but a little,
But the five
plus
is
five.
not gonna kill us?
No.
All right.
Okay.
All right, so we're gonna look specifically today at using the complexity of renewable energy in a unique way as a benefit and not as a deficit. So
Just put it right there.
what that means is we're gonna define better in terms of affordable and reliable. Current roadblocks, as already been mentioned many, many times, is the US electricity is already cheap and reliable. However, even though that gets framed a lot in policy of who already has cheap and reliable electricity, we're gonna show that that may not be the best starting point that you should start at, and we'll get to that later. Most people are discussing the status quo with adding solar, wind, batteries, and the adoption tends to be slow right now, even though we're facing a potential sixth extinction. So I'm going to pass it off to my colleague, who's going to start kind of introduction to where we started, and then we'll go into the modeling and then the results.
So one of the motivations for this research is the problems with current incorporation of renewable energies. And specifically with solar energy, as you may have heard, there is a deficit as the sun sets, because after the sun sets, that's right about when people require the most energy. So if you use solar straight onto the grid as it's sunny, you have to ramp up with a lot of different energy sources, which can often be inefficient and negate the benefits that you would have gained from using solar power. And this solar deficit, you can see, is only going to increase without the incorporation of storage. This is for California. And unless we incorporate storage, it's only going to get worse. Now, a sort of brute force approach to the incorporation of storage would be to just, as you generate enough solar energy, store that in batteries and then use it as people require the most energy.
Who has never heard that before? Right, we're in energy. We all know this issue, right? 101, yep.
Right, and now I'm going to hand it off to Professor Mecklenburg to talk about our solution.
Right, so this is kind of the traditional, what I would call Newtonian mechanics, duck effect for energy, right? But if we want to look at complexity, then we're talking about moving into systems that are not the classical systems. So this happens to be an image that I like, that's a fractal from James On. Since Bobby loves the duck curve and always begins it, I said, yeah, but what really matters is incorporating the complexity of renewable energy. So that's very specifically what we're going to focus on. We still model the status quo solution and compare these other models and solutions to the status quo, but we want to specifically focus on modeling and optimization algorithms. So for designing complexity for affordability and reliability, we're going to go over this a couple times because it gets complex, obviously. So in each system that we consider, we are going to consider an A system, which is the startup system. Most people design, unless you're in the utilities industry, for one system. If you're in utilities, you know you don't have one system. You have a system and a backup system. Most people designing energy systems are not designing for backups, unless you're in utilities. So model B is always considering some aspect of a backup system. And predominantly we're focusing on wastewater treatment plants because we already have in existence many wastewater treatment plants, which means they already have a digester, they already have heating to the digester to have the process of turning it into methane quicker, and it's very cost effective to add on a biogas digester. Does anyone know the dollars per kilowatt hour for a wastewater treatment plant to add a biogas digester, order of magnitude? Just out of curiosity. So we have the citations at the end that we can show you, but would you believe me if I said 1 to 2 cents per kilowatt hour? It's pretty cheap, right? So many wastewater treatment plants are seeing this as an ability to make money by adding an extra product that they sell with the utilities grid. So in every one of backup B, we're looking at wastewater treatment plants to meet some, let's say, deficit of our Model A. So we're going to go in 3 scenarios. Scenario 0 is what most people talk about, not necessarily energy experts, but let's say journalists and my uncle and aunt who are always talking to me, the kind of status quo, if you will. So solar, wind, battery. Scenario 1 is what I call, or what we call, the high income country approach. And this approach says, if we can do some sort of control, model predictive control, some sort of forecasting in the future, some sort of understanding not only of what we plan to do, but also the uncertainty of what we're going to do, then we're designing for systems that are pretty high tech. Okay, so I'm calling that we're calling that high income country scenario. However, I have a lot of experience in low to middle income countries, specifically in electricity and healthcare. And the way that they are forced to design system is going to lead to an interesting result that we completely neglect. And so that's what we're going to focus on today, is comparing these different scenarios. So again, predictable versus unpredictable, high income country type approach, capacity shortage versus over-design, low to middle income country approach, and we will specifically talk about that. So,
Yes, so I'm going to talk a little bit about analysis, the first analysis pathway, scenario 1 that we did. So one way that you can sort of get the predictable values of your power demand is you can take the fast Fourier, through Fourier analysis, you can take the fast Fourier transform of your data, and what that'll give you is the most prominent frequencies in your data. So some obvious ones that'll come out is the day, the year, seasons, the work week, and that's simply because people use more electricity during the day than at night. People use more electricity during the summer than winter, usually, if the air conditioning costs are high. But there's a lot of ones that you couldn't easily deduce that you can get out easily through fast Fourier transform. And then what we do with these predictable frequencies is we model those with solar and wind and batteries, and then with that, what we don't model with that, we then model with biogas, which is very cheap.
okay, just to tag on that, just to be clear. So you can do a fast Fourier transform of any signal. Then, if you take, in our case, the top 25 amplitudes, you can then create this light blue curve. Apparently MATLAB calls this sine whatever. So this is what we would consider the predictable power load. You can then subtract the predictability from the actual measured. And in this case, this is the absolute value of the error, in other words, the actual versus the predicted, and we call that our uncertainty. So here are 3 examples of uncertainties. We need to understand the power load. So this is 8,760 hours in a year, and then the level of the power load, but we transform this into what's called a DMAP. So this is 24 hours in a day, 365 days in a year. This is the same data, just plotted differently. We can then look at the predictable inverse fast Fourier transform of the first 25 amplitudes and look at the unpredictability and look at that. This goes from negative to positive. Look at that as the positive power and the negative power and try to understand what this uncertainty is and how it drives the system in different ways. You can do a similar thing with solar, but solar is very strange with FFT because at night it's 0, which has no cycle to it. If you cut out all the zeros and do a predictability of the non-zeros, you can then do an FFT to IFFT analysis, and it will look like an I because that's the summer, depending on where you are. Obviously, if you're near the equator, it doesn't look like an I. It's fairly flat. If you're way up in Russia, it really looks like an I. Yeah? All right. With wind, this is the wind data of a sample city. So you can kind of see the distribution of the wind throughout the year. This is then the DMAP. This is the predictability. This would then be the unpredictability, right? This minus this gives you this. And there's negative and positive of these values.
So this kind of is a flowchart for what leads to scenarios 0 to 1 and to make it a little easier to understand. You see, for scenario 1, what we're doing is breaking up the original power load, the original solar radiance, and the original wind speed into the FFT, what we call the predictable, and the IFFT, what we're modeling with biogas. And then you can decide what storage devices are needed for each of those. And now I'm going to hand it off to Brady to talk about the final analysis pathway.
So, like we were just talking about, there's the different scenarios. And starting out with scenario 0A is the traditional wind, battery, solar panels that we put in the real data into. And that's kind of the base load that or the baseline that we're comparing everything else to. So then there's scenario 0B, which is the status quo but with added biogas and still with the real data.
So that would be the revolutionary idea. Let's just add biogas to wastewater treatment plants, but we're looking at additional things. Yeah?
Yes, yeah. So now starting to take some of that predictability into account, we have the scenario 1, which you take system A, which is based on the predictability, you optimize that, and so that gives you, Homer Energy gives you the system architecture, so how many wind turbines specifically, how many batteries, how many solar panels, what size inverter you need. And we then took those numbers as fixed and then incorporated them as the baseline of system 1B, but then we allowed the biogas generator to be variable to get the uncertainty so that at the end of the day, it was 100% reliable, even with the quote real data. So that's just kind of pictured here, where on the left-hand side you have the predictability feeding into system 1A, and then on the right-hand side you add the unpredictable parts and feed that into system 1B using what's held constant from 1A, and then that gives you the total scenario 1 cost in terms of dollars per kilowatt hour, how many wastewater treatment plants you need, what size that is. Yeah.
Okay, so, and then in scenario 2, what we find, and I'll talk just very quickly about that, is because of economic constraints, people accept a capacity shortage all the time in low to middle income countries, and they have to, they're forced to. And so we just said, well, what if we design a system for a capacity shortage whereby we save 50% of the cost, and then design a backup system? Is that going to be a wash, or do we save money, right? What happens there? So this is an example from previous research, and this shows that this paper that was designed for Iraq, healthcare center in Iraq, was chosen optimal with only solar battery converter and healthcare load to be an energy capacity shortage of 80%. Now, they could have added a generator, but if you read the academics who wrote this paper, they give a fairly compelling socio-technical and sociological and just geological context for where this healthcare facility is, of why it makes no sense to do a backup generator. If you did, every day the electricity would be on, right? Because you have a backup diesel generator. However, they say, oh, let's just accept a 20% capacity shortage. In this case, it's 18. What does it look like? Well, they never looked at it. They never looked at the time capacity. So I work on a set of papers associated with the healthcare consequences to that. But this is what that looks like. Is the failure happening at night? No, right? The failure's happening in the middle of the day. Yeah? That's when the power load goes high. At night it's low. So, the very time in which you need electricity, you're not having it, and in fact, 25% of the time, that healthcare center will fail. If you know of the hospital designed and installed in Haiti, and how they went from here to here very quickly, you know exactly what I'm talking about. But let's look at designing a backup system just for these failures. What does that look like? Well, we already know from previous literature that by accepting a 20% capacity shortage, you can save 50%. No, 50% is a lot. So would the backup system cost that amount of money? So here are some sample examples, and we're going to try to get done in 2 minutes.
Sweet. Thank you for that challenge.
We're almost there.
So the first example that we have is Boise, Idaho, and also just as like a clarification, that 50% savings doesn't necessarily always come at 20% capacity shortage. For some of the cities that we looked at, it could come in at as little as 1%. It was just that peak 1% required way more cost. So it varied anywhere from 1% capacity shortage to 20% capacity shortage for the cities that we looked at in the US. But yeah, as an example, there's Boise, Idaho. So the top left will be the status quo, and then everything on the right-hand side will be the total system 0B or total system 1, total system 2. And so we also have neat little arrows illustrating the savings across going from 0A to 0B, and then from 0A to 1, and from 0A to 2. So you can see that there's a 2% savings going from 0A to 0B, a negative 12% savings from 0A to 1, and that happens sometimes, but there were also other cities where system 1 was the best system. So we'll get to this later, but which scenario was best depended on which city and kind of what resources were available there, what the load looked like. It wasn't a one-size-fits-all solution. Looking at Charlotte, you now have a 12% savings by incorporating biogas, another negative 12% savings using the FFT, but using the capacity shortage, you have the 35% savings, which is the greatest for this city. Nashville, you now are seeing a bigger savings from going to System B at 24%. We're finally seeing some savings for System A at 22%. And again, you're seeing the greatest savings in System 2, System 2 here with 52%.
So how does that look if we were to summarize? So if you look at the cities and you say, we're just going to design the status quo system, solar, wind, biogas, and you do that, how many of the systems, in terms of levelized cost of electricity, this is the most cost-effective system, 4.5%. If you add wastewater treatment plants, how many of the cities are the most cost-effective for that? It's 9.1%. If you design the system using high-income countries' assumptions, so doing this predictability and noise type framework, so the people who are very interested in model predictive control or other types of forecasting systems, it is true that 27% of the cities that we considered do have the best benefit by understanding what the future is going to do, having an understanding of predictability and your uncertainty. However, the most shocking thing is if you increase the capacity shortage until you reach 50% cost savings, and then just design a backup system for that, 59% of our systems are more cost effective, and I don't know anyone in the world besides my colleagues who are doing amazing things in the places that I work, does this. So that is our result and what we're looking at. We're looking at this idea of we have a lot of complexity in renewable energy, but if we look at this complexity, it can be a benefit. It doesn't have to be a deficit. And now we're open for questions, and we were 2 minutes over what we were hoping to 5. Sorry.
All right, thank you. Maybe I would suggest maybe the next presenter to upload your slides while we take a couple of questions. So questions?
Fascinating work. This sort of 50% cost savings, I guess this is just a hand-picked number, because I guess there would be some kind of a sweet spot for different configurations where this is even better.
Yes.
So
That is as a physicist, I would call that my, next level of accuracy that I'd want to look at, right, is to consider those trade-offs and to find that sweet spot. But there's a lot going on. This data set alone is how many data points? Around 13 million?
Yes.
Yeah. So once we start varying all of that, every single one of those that we vary is going to be another 13. Correct? We have an idea, but we don't have a robustness for the answer that you're looking for. Yeah. We have more, what do we call it? An engineering rule of thumb based on doing this many times.
just thinking, it would be interesting to see, are there optimal solutions with 80% savings or whatever?
Yep. Yep. Thank you.